field though, it's keeping the focus.
Yeah.
My name is RENAUD De Richter. I work as a scientific advisor for methane action, and I am a chemical engineer and with a PhD on organic chemistry. Yeah, in fact, I moved to climate after working on renewable energy, and 10 years ago, or 12 years ago, I started working on greenhouse gas removal. And we published several articles about removing them by photocatalysis.
Okay. If you could say this, answer this as a statement, but you know, the drive towards net zero and the public awareness of net zero and the public generally thinking that net zero is all we need to do. Could you just explain that that's not the case?
Yeah, net zero will not be enough because the warming will keep up, melting the ice in the Antarctic and on the Greenland, and sea level rise will continue. So we need to go further of net zero, and we need to come to pre-industrial levels of greenhouse gases to stop sea level rise.
Yeah. What attracted you to focusing on methane?
Yeah, in fact, we noticed already 12 years ago that methane was very important, but the public awareness and the policymakers didn't realize that methane was so important, and all the public discussion was about carbon dioxide and carbon dioxide removal and carbon dioxide mitigation and getting off of the fossil fuels. But methane really became very important in the last 2 years thanks to the IPCC, the last IPCC report, the sixth one, and also by the Global Methane Pledge last year.
Can you just give us a couple of overview points about methane as far as it being infinitely more powerful but rarer, and just some of those key points?
Yeah, in fact, methane is a greenhouse gas like carbon dioxide, but its warming potential is much higher than carbon dioxide. On a 20-year basis, it's about 86 times sorry.
Oh, let's start that again then.
Yeah.
They're just the distinguishing points about methane.
Oh, sorry, repeat.
Well, just tell us some of the characteristics of methane.
Okay, so methane is a greenhouse gas, much more powerful than carbon dioxide. On 20-year basis, it's 86 times more powerful. And what is attracting in methane is its short lifetime, because it's only between 8 and 12 years lifetime. So we can act on methane, and we should act on methane, because right now the global warming due to methane is 0.5 degrees Celsius, and the carbon dioxide is only about 0.8. So methane is really the second most important greenhouse gas, and acting on it, we can reduce temperatures.
What are some of the dangers that methane presents at the moment, and maybe just talk about the human methane activity, but then you know, industry and so forth, but also the global warming and the fact that that's creating the potential for a time bomb?
Yeah, methane is also very dangerous because of the possible methane time bomb, as it was called by some journalists. The permafrost is thawing, and there are huge amounts of carbon stored for several thousand years. And after thawing permafrost, this carbon will be released as carbon dioxide and methane. And methane can induce vicious circle. More methane released will induce more warming, and then more warming will release more methane. So there is a feedback loop, and also there is a very high risk of destabilization of the methane hydrates, which are submarine, and the reserves are huge all over the world, all over the coasts.
Can you just distinguish the difference? There's natural methane release, and then there's human-created methane release, you know, through industrial agriculture and things like that.
Yeah, for the moment we are distinguishing both. More or less 50% is released by human-made activities like agriculture, rice paddies, and meat production. Also by the oil and gas industry, but other release of methane, about 50%, is considered as natural, as biogenic, because coming from wetlands or from ponds and lakes produced by microbes. But in fact, global warming is man-made, and this is accelerating and increasing these natural methane emissions.
Can you talk about, you know, there's, as far as the man-made stuff, you know, we can mitigate, we can reduce, which is what we need to do, but it goes beyond that. So I want to lead into restoration as opposed to mitigation.
Yeah, in fact, restoration is much further than mitigation, because even if we succeed net zero, it will not be enough. So we need to restore the levels of greenhouse gases to pre-industrial ones to stop sea level rise. And so climate restoration is really essential if we want to preserve the avenue for our grandchildren.
Can you just give me another definition of restoration, just for the general public, saying that, you know, there's, you know, the methane mitigation is reducing, but this is about removal.
Right. So climate restoration is about removal of greenhouse gases, and you need to, for carbon dioxide, to store it. But for methane, you need only to transform it into another thing, which is much less dangerous for the climate and induces less warming. And as a matter of fact, it is easy to remove methane, more easier than carbon dioxide, because it's so powerful that removing little amounts of methane has a very important effect on the climate. Right now we are in a methane emergency. The last year's IPCC report showed the real importance of methane. In fact, more than 1/3 of current warming is due to methane alone. And methane warms the Earth right now by 0.5 degrees Celsius, which is more than 0.9 degrees Fahrenheit. And in the last 2 years, 2020-2021, there were the largest atmospheric growth of atmospheric concentrations of methane.
Okay, so slide 3, the permafrost time bomb.
Yeah, accelerating permafrost thawing due to global warming will release huge amounts of methane and carbon dioxide. And this is considered as a possible methane time bomb.
You know, I think instead of me, this is great, just go.
Okay.
Work your way through all the slides, and then you can use this as a presentation as well. So.
Okay. And there is also another time bomb, which is the destabilization of methane hydrates, which are submarine or all along the coasts, and the reserves of methane hydrates are much higher than the reserves of coal on land. And that's very scaring. If destabilization occurs, that will induce a feedback loop, which is very bad for climate. Do you think that I do the presentation, you mean? All the Because then there is the global methane assessment, which is from the United Nations.
Yeah, just go through it all, because I can just take it out if we
Okay,
don't use it.
good.
Yeah, yeah.
Okay. So the problem of the methane emergency is that the new methane emissions are increasing. The net methane removals by natural processes are decreasing. So the stock in the atmosphere the stock of methane in the atmosphere is increasing. And the global methane assessment published last year by the United Nations and the Climate and Clean Air Coalition shows that in the baseline scenario, in the baseline case, methane emissions from human activities are expected to continue rising for the next decades. It ranges, depending on the scenarios and the climate models, from 0.7 to 1.5 degrees Celsius. But by the end of the century, in average, the methane can contribute alone to 0.9 degrees Celsius of warming. So the United Nations, as well as the Global Methane Pledge, propose to reduce methane by anthropogenic emissions of methane by 30% or by 45%. And of course, this is very difficult reductions to obtain, and we don't know how much the natural emissions will be. So methane removal is necessary. There are some bad news and some good news. The bad news is that the atmospheric concentration of methane is rising faster and faster. Also that the oxidative capacity of the atmosphere will be reduced when we get rid of the fossil fuels, because there will be a reduction of the nitrogen oxides and other oxidative pollutants that increase the oxidative capacity of the atmosphere, and so increase also the removal of methane. And also, as already said, the biogenic emissions of methane are increasing faster and faster due to global warming, and so they are considered natural, but in fact they are due to global warming. There are nevertheless some good news and some reasons for hope. The Global Methane Pledge that has been signed so far by more than 120 countries targets to reduce by 30% the anthropogenic emissions by 2030 compared to 2020. And there are several promising methods that can deal with the reduction of the oxidative capacity of the atmosphere. So the good news is that the warming feedback loop due to methane can be prevented, and we can also get prepared to a possible methane burst. But methane removal cannot act alone. It's complementary to methane mitigation, and both can succeed bringing back methane to pre-industrial levels, and that will shave peak temperatures in this century by about 0.6 degrees Celsius. This is possible to reach. The natural methods by which methane is removed from the atmosphere is just by oxidation. One molecule of methane plus oxygen will give one molecule of carbon dioxide plus water, vapor. And of course the chemical reactions are more complex than that. But our goal is just to speed up these natural oxidation processes with great benefits for climate, because the global warming potential of methane is so bigger compared to the global warming potential of carbon dioxide. The principal methods, the principal things of methane in the atmosphere, in the natural processes, are the hydroxyl radicals, which are named the detergent of the atmosphere because they remove all the volatile organic compounds, including methane. And another thing is methane-consuming microbes, which are on different supports, on plants, on trees, on surfaces, and on land, on soil. So the scientific articles that propose methane removal methods are three different methods, three different ways to do that. The atmospheric way, the microbial way, and the technological way. The natural atmospheric way is by enhancing the natural sinks of methane, the hydroxyl radical and the chlorine radical. That can be directly performed in the atmosphere, because the natural diffusion and the mixing with the air will take place, and there will no need of capture or sequestration. The second natural way to perform it is by microbiological ways, and we can enhance the amount of microbes which consume methane, or we can inhibit the microbes that produce methane. And last but not least, the technological methods that speed up the natural oxidation of methane use, for instance, catalysis or catalysts, which have already proven to be safe and effective in the laboratory. For instance, for enhancing the chlorine radical sink, we only use sea salt, which with the natural acidity generates hydrochloric acid, very, very slow levels, but it is a natural process. And the sea brine mixed with very little amounts of iron. Iron is a catalyst. Under the sunlight, we produce chlorine radicals, which then oxidize the methane. And the fact is that chlorine radicals act faster than hydroxyl radicals, 16 times faster. That's why this sink is very important if we can enhance it. And a possible way of dispersion of the sea salt and the small amounts of catalyst of iron could be thanks to the shipping industry. The ships burn bunker fuel, which contains small amounts of iron, and when this iron is released in the atmosphere, it mixes naturally with the sea brine and with the sea salt contained in it, and this produces these chlorine atoms, which is a catalytic process. Okay. And we can enhance this sink by adding some more fuel additives to prevent pollution and to remove. So there exist already fossil fuel additives which reduce the consumption of the ships and reduce the emissions of black carbon and other pollutants, but also will release a little bit of iron and will enhance the chlorine sink. The enhancement of the microbiological sink can be done also using iron sulfate. Iron sulfate is considered as a fertilizer, and it increases the yields of the crops or the fruit trees, and it also used as a medicine when plants suffer from chlorosis. So adding iron sulfate is something that is already very used all over the world, especially when you have alkaline soil. And by increasing this amount, we can inhibit the methane producing microbes, but also enhance the methane consuming microbes. Concerning the technological solutions, methane is very diffuse in the atmosphere. Its concentration is only about 2 parts per million, and that's because it's so potent compared to carbon dioxide. This concentration is lower. So we need to treat large volumes of air, and this can be done either using devices that are exposed to large volumes of air, such as catalytic coatings on buildings, infrastructures, and vehicles. Or we can use air-moving devices, which are passive ventilation systems used by the architects. We can also use other devices which process large volumes of air, and one of them is the solar chimney. Solar chimneys are very large greenhouses which warm the air below them by greenhouse effect, and a chimney in the center of this greenhouse which drives the air outside. So the air enters by the periphery and gets out by the top of the chimney. And those solar chimneys were developed to produce renewable electricity, carbon dioxide free, but they can also be used in synergy with greenhouse gas removal, and in particular with methane removal, because we can coat on the glass of the greenhouse, we can coat very small amounts of catalysts which will oxidize methane into carbon dioxide, and there will be no pressure drop, so the electricity production by the solar chimney is not perturbed. So we know how to generate hydroxyl radicals, which are the detergents of the atmosphere. We know how to generate chlorine atoms. We know how to inhibit methane-consuming microbes, inhibit methane-producing microbes, enhance methane-consuming microbes, and we know also how to activate mineral surfaces to oxidize methane, thanks to the sunlight using photocatalysis. But we will need to process very large amounts of air, and none of this will be done easily, because the problem of global warming has been created during more than 1 century, and we have very few time to try to solve this very big problem. So big problems need big solutions. As a conclusion, thanks to methane removal and to aggressive methane mitigation, we can keep within reach the Paris goal of temperatures below 1.5 degrees Celsius, and we can succeed bringing back to pre-industrial levels the concentration of methane, shaving the temperatures by 0.5 degrees or 0.6 degrees by the end of this century. But we can also be prepared to deal with possible methane bursts and to help prevent a methane feedback loop. As a conclusion, for all these reasons, methane removal deserves funding. Thank you for your attention.
Okay, cut both cameras. You concluded in your presentation saying that these are reasons why we need to fund it. Can you just focus on that a bit more? Just saying that the costs required for this are nothing compared to some of the other ideas that are floating around. It's doable. It's realistic. It just needs the will to fund it.
So methane removal, all the methods are really something that is scalable, faster, and the atmospheric or the microbial ways to remove methane, to reduce the amounts of methane, is much cheaper than any other method that has been proposed, for instance, for carbon dioxide removal. And even the technological methods seem cost competitive, because not only you produce electricity, but you can also remove greenhouse gases, methane, but some others also. So we really need to start funding on this, and the public awareness of the importance of methane, and so policymakers I start again.
Yeah,
so
yeah, sure.
all the awareness of the policymakers of the importance of methane just come out in this last year and this last 2 years, and I'm really optimistic about the fact that we will act faster, and thanks to the action of Methane Action, an NGO that was created 1.5 years ago, which has communication skills better than the ones of the scientists such as me, will probably, and I'm very confident that we can go faster and faster for this research development and also for the implementation later on. And as I said, it's much cheaper for the first calculations, even if the figures for the moment are too early to be sure of them. It's about 100 to 1,000 times less than for carbon dioxide removal. But of course, both will be needed, methane removal and carbon dioxide removal.
Can you say, if you agree, something to the effect that I just want to create this positive sense of the train is moving, it's happening, you know, the research is being finessed, there's been proof of concept models, even if they're not exactly specific to that, but things are happening with methane removal. It's a reality, and it's happening. We just need the will to fund, to scale.
Methane removal technologies have been proved at the laboratory scale, and things are already moving and getting faster and faster. We are really confident that the scale-up will come sooner, faster, right now that the consciousness of the policymakers and the funders has started, and they already put a lot of money on direct air capture and the other technologies of carbon dioxide removal, and I'm very confident that they will soon fund methane removal.
Just talk about where we are on the planet as RENAUD, just as a person with a wife living in a beautiful city, and how you see the future. We're in a mess, but there's possibilities. How do you feel?
Yeah, right now we are, as I already said, on a methane emergency, but I really feel confident that we will preserve our environment for our child and for our grandchild. And we live with my family in the south of France in a very nice and beautiful environment near the Mediterranean coast, and we want to preserve it. So methane restoration and climate restoration are really necessary, and I am really confident on future.
Oh, that's wonderful. Okay. I just want to simplify a couple of quotes and statements in connection with the PowerPoint. Could you give us a statement around the methane removal methods are pretty much replicating what nature does. There's nothing Frankenstein about this.
So biomimicry?
Biomimicry, yeah, sure.
Okay. So all the methods of methane removal that are proposed on the scientific literature are just trying to accelerate natural processes that already exist. It's like biomimicry, and so it's just enhancing them, accelerating them, but the nature has proved that they are safe, so we believe that even if of course we will need environmental impact assessments, we believe that there will be absolutely no problem and that we can implement them quickly.
Okay, that's great, yeah.
Yeah, methane removal is based on 3 separate approaches. One is the atmospheric one, enhancing the natural sinks of methane, like the hydroxyl radical or the chlorine radical, which are the detergents of the atmosphere. The second one is the microbiological approach, which is enhancing methane-consuming microbes and inhibiting methane-producing microbes. And the third one is the technological one, which requires processing large volumes of air on catalytic surfaces.
Yeah, thanks.
Methane removal has come to a reality thanks to catalysts, people who are activists and see the real importance between the scientists and the policymakers and the NGOs. And one of them is Peter Frykowski, that is a visionary, and he's also an activist, but he really created the bridge and the link between all of us, the scientists, the NGOs and the policymakers. And thanks to him, the Foundation for Climate Restoration and Methane Action exists, and some others also. And it's really important to have this type of catalysts.